Hi, the title of my today's talk is Learning Contraction Policies from Offline Data. I'm Navid, and this is a joint work with my colleagues at University of California, Irvine and University of Illinois, Urbana-Champaign. Sometimes we are handed a complex dynamic system like a drone and we are asked to control it, but we are too lazy to go through modeling the dynamics of the system and accounting for all possible uncertainties. But we are not that lazy to not gather data from the system. We can initialize the system in different conditions and inject random inputs and observe the state outcome. Finally, by putting all these trials together, we have a data set describing the dynamics. Now, what we are driven to do is to utilize the data set encompassing our dynamics to come up with feedback or state-dependent control policy to steer our complex dynamic state to a desired state. What we propose in our work is to first learn a model of the dynamics that best describe the control input dependent state transitions of the dataset. Then we learn a control policy to control the learned model. We also want the same policy to be effective on the main dynamics too. What we propose in our work is to design a control policy that when it's combined with the learned model, it enforces a local property at the data points at which the learned model is expected to be closest to the dynamics, and essentially resulting in a global target tracking behavior. And the local property is contraction. It simply says that if we propagate any two close state points and observe their weighted distance shrink with respect to a weighting matrix theta, we can say that all trajectories of the dynamics converge to each other and to a unique trajectory. So we have our state data points available, but they're not necessarily close enough to each other for contraction theory framework. So what we propose is to sample close points to each of the states in the data set to augment our data set. Now we have a data set usable in contraction theory. A control input enforcing contraction policy makes sure that all generated closed data points in the augmented data set gets closer when propagated. And of course, they get closer in the sense of their weighted distance given matrix theta. Now the problem is that both control policy and also the contraction matrix are unknown. Let's first assume that there is a contracting control policy, but the contraction matrix is unknown. We can learn the unknown contraction matrix by first defining a parameterized matrix theta, and then make an attempt of learning the metric by minimizing the amount of contraction seen in the augmented dataset. And of course, the control policy is unknown, so we propose to learn both parameterized control policy and the parameterized contraction matrix simultaneously. Our proposed cost function implies that we have a learned dynamics and we propagate the closed data points in the augmented dataset by control policy. And with contraction matrix, we measure how good the control policy is doing. Since we don't know if the control policy is doing a good job or contraction policy is measuring well, we learn both of these at the same time. Essentially, we are enforcing contraction locally at each data point of the main data set, and we expect to see convergence of all trajectories to a unique trajectory. But the trajectories may not converge to where we want them to converge. So to solve this issue, we add a steering term to the loss function. This steering term tells the controller, besides forcing the contraction on the system, it should make sure to drive a limited number of states to a desired state in case steps. So we're steering our dynamics. So we implemented our proposed algorithm on a model of a drone and compared it with when we don't have contraction, and we compared it with MPC ILQR, and we also compared it with CQL. And as you can see, our method beats other in the sense of tracking error. What we proposed was enforcing contraction locally at a limited number of data points, but we don't know if we are having contraction at other points or not. So in future work, we will study formal guarantees on this matter. On the points that we don't see in our data set, we want to see if we have contraction or not.